Okay, what's up everyone? Welcome back to another fun day of proof, set theory, and logic. Let's do it. Yeah, proof, set theory, and logic. Yeah. Woo. All right, we're in chapter 2, logical arguments, and we are in section 2.1, rules of inference. So, really quick, just to remember where we were at last time, let's put out this table. So, recall, we had a couple of really nice places to start. We had, actually I'll even just write this table here with no recall. I'll go name of the rule, hypothesis that we have, and the conclusion we can draw from it. Okay, so we had a whole bunch of different ones of these. First off, we had modus ponens, an interesting name. This had P, and P implies Q, and our conclusion from that was Q. So if you want to remember how all this worked, we'll use this first one just as a good example. The whole business of it was, hey, suppose your two hypotheses have the truth value P. That is, suppose they're both true. The claim is that if both of these things are true, then this thing has to be true. Does that make some sense? Yeah? Remember this business? Okay. So it could be the case that some of these things are perhaps not true, in which case you would not be able to derive the conclusion, right? But the structure of a propositional argument says, if you accept that these things are true, you must accept that this is true. That is, the only way to dispute this conclusion is to say one of those things, at least one of them, has to not be true, right? Okay, so the structure of propositional argument is basically kind of like arithmetic for propositions. You say, if you have these things, you put them together, here's the new thing you get out that you know is true. Cool. First one, modus ponens. We saw that last time. We said modus ponens says if you got P, and you know that P tells you that Q is true, then Q has to be true. Yeah? P and P implies Q implies Q. Okay, we had modus tollens. Oh, only one L. I always put two. This says not Q and P implies Q. Well, this tells you not P. Basically, modus ponens on the contrapositive, right? Okay, cool. I'll put the rest of them up here really quick. We talked about these last time. There's the hypothetical syllogism, which says that, hey, P implies Q and Q implies R. Well then, P implies R. Okay, reasonable. Thing 1 implies thing 2, and thing 2 implies thing 3, then thing 1 implies thing 3. All right. Addition, an easy one. Addition just says, hey, if you've got P, then we may conclude P or Q for any old Q you want, right? All right. Simplification. Simplification says if you've got an and, you can just get one of those things. That is, if you have P and Q, you can certainly get P. You could also get Q. Same business. Okay. Ooh, have I lost connection on my audio? Maybe. No. That's back. There we go. Good. Okay. No more technical issues. Conjunction. Terrible marker. And disjunctive syllogism. Are our last two. So in conjunction, we say, hey, we've got P and we've got Q. Well, then we certainly have P and Q. Gosh, that one looks silly, right? But it says, hey, if you've got two separate hypotheses, one of them is that P is true, and one of them is that Q is true, then you can conclude that the statement P and Q is also true, obviously. Disjunctive syllogism says that if you've got P or Q and not P, then you can conclude Q. Okay, a lot of little pieces, a lot of little named things. you might say to yourself, how am I ever going to remember all of these? And the answer is by using them a lot. That is, you could make yourself some flashcards to try to remember these, but you really don't have to. We're going to do this enough that you will get super used to doing it. It will be like second nature for you. Okay, cool. So if you recall, here's kind of the idea of how to do propositional arguments. So last time we did a little example. And I said, how can we express these in a notation that is nice? So we said, let's express modus, let's do modus ponens. Or no, I think we started, did we do tolens last time or ponens?
We did both tolens and ponens.
We did tolens, okay, cool. Well, let's just do tolens then. Express modus tollens as a propositional argument. So, quick little refresher, I won't make you do both. The solution here is just to write it out like you're doing addition in like first grade. So you say, hey, modus tollens, this tells me, oh, let me write this right, not Q, and P implies Q, and then I say, therefore, this little 3-dot symbol, I don't know why we decided the 3-dot symbol would mean therefore, but someone did, so we'll keep it. Therefore, not P. Okay, reasonable perhaps. Kind of see the way you do it. You can, some people like to, right justify things, left justify things, try to put similar things over each other. I find it useful personally to try to stack variables that are like the same, right, from line to line. Okay, so here, you get a chance to try it really quick. So we did ponens, we've done tolens, express the rule of hypothetical syllogism as a propositional argument. Okay, give it a shot, see if you get it. I swear it is as easy as you are expecting it to be. P implies Q and Q implies R tells you P implies R. Is that what you got? If it is, cool. If you decided to be fancy and try to write it like this, I guess there's no stopping you. But I would say that if you really, like, you can do this, but it starts to get a little bit, it can be a headache, right? It can make these things start to really stretch super far away from each other. So at some point, you gotta sacrifice the nice like flow structure of it, right? But hopefully it's still relatively clear. Okay, cool. So we got some good stuff there. Now, let me go back to the black marker. I think it's giving me better contrast. Now, well, there we are. Dropping markers. Now we want to describe which propositional arguments are good ones. So we'll introduce a definition. We say a propositional argument is valid if accepting the hypotheses forces you to accept the conclusion. Now, the phrasing of this is perhaps unfortunate. That is, you could still just stubbornly deny the conclusion even if you have, accepted the hypotheses. And if you've ever gotten an argument with somebody who's stubborn, then people love to do that, right? You can present the argument and they'll go like, I don't know, man, I just don't buy it, right? It's kind of a classic thing people like to do. So maybe it doesn't actually like force you in any sort of literal sense, but at least in some sort of like a logical sense, like if you constructed a truth table, you'd go like, you got me there, right? Don't ever try to construct a truth table if you're having an argument with somebody. It'll just make them mad, right? Not a good move. But okay, let's see if we can prove that a propositional argument is valid. One, perhaps, that is not in this table. Let's see if we can use some of the laws in this table to prove a propositional argument. And let's see if we can do this without having to resort to a dang truth table, right? That is, pressing my button so I go back over here, you could perhaps accept, hopefully accept, that all of these rules here could be proved using a truth table. That is, if you want to show modus ponens using a truth table, you would do something like this. You would say, hey, modus ponens using a truth table? All right, let's just do it really fast. It's nothing too complicated, or in all honesty, it's nothing too interesting. But if you wanted to prove modus ponens, which says P and P implies Q, then all you'd have to do is go, and that marker is fully dead. An unfortunate dearth of good markers out here. I hate when that happens. All right, so you would say, all right, let's put P, let's put Q, let's do our usual business. I would say P, true, true, false, false, true, false, true, false. And then I would go P implies Q. Everyone remember this one? What's the business? Yep. True, false, true, true. The only time the statement P implies Q is false is if P is true and Q is false. That is, if it's not the case that having P be true tells you that Q is true, right? Okay. So the statement of modus ponens is that if P is true and P implies Q is true, so too must this one be true. So all you really have to do is go through and get rid of any of the rows where one of your hypotheses is not true. Yeah? Okay, so here's a row where P is not true. Here's another row where P is not true. Erase. Boom, boom. Okay, now let's take a row where P implies Q is not true. Oh. Hey, wouldn't you know it, if P is true and P implies Q is true, then so too must Q be. How about that? So you can see basically showing a rule of inference of this form boils down to writing the truth table for all of the involved statements, then erasing rows where all of your hypotheses are not true. Then what you should get back is that all of the conclusion columns have only t values. Reasonable? Okay. So you can imagine you could go through and you could show all these in the standard kind of fashion, right? You can construct truth tables. This is actually perhaps easier than constructing truth tables. It's like building a truth table, but you don't even have to care about all of it, right? Okay, so it's even better. The idea of what we're going to do now is that we're going to take these little pieces and we're going to put them together to prove more complex arguments without having to appeal to truth tables anymore. That is, if you accept that these rules of inference seem reasonable at this point, if you buy them, right, or if you at least buy that you could go through and prove them using a truth table, then you hopefully can buy that we can use them to justify steps in starting from some hypotheses and ending at a conclusion. That is, we will move from the hypotheses using these rules of inference to produce our desired conclusion. And each step will be justified by appealing to a rule of inference. Cool? Okay. If you want to think of it, it's like we're, instead of doing the whole truth table for a potentially extremely complex statement, right? What we're doing instead is we're saying, hey, if I start with these pieces, here are some easy steps. Each of them provable using a truth table in a relatively simple way, that is, some rules of inference, and at the end we produce our desired conclusion. So let's do an example. Here's an example. Prove that the following propositional argument is valid. So here is the argument. P implies Q, and Q or R implies S, therefore S. You can already probably feel yourself going, ugh, if you like think about making the truth table for this, right? It's going to be annoyingly big, yeah? It's going to have a lot of rows. Confusing to put all together. So let's do it a different way. Let's do it the way we just described. So here's how we'll do the proof. What we'll do is we'll do it in like a nice numbered format with justifications for each step. So step number 1, we'll say, all right, I've got P. This is one of my hypotheses. So my justification for this statement is that it's one of the hypotheses, right? P is true. That's one of my hypotheses. It's the first hypothesis. Yeah? Okay. So next step, I'm going to say, hey, P implies Q. Well, that's my next hypothesis. Right? Reasonable yet again. Now, is there anything I can use, say for instance something where you start by assuming P and P implies Q and deriving a new statement from it that we could appeal to? A rule of inference, perhaps. Modus ponens. Oh ho, ponens to the rescue. Yes. So if you've got P and P implies Q, then you've got Q, right? Q. This is modus ponens on 1 and 2. That is my justification for that step. Reasonable? That is, we explicitly stated which hypotheses we're using. We justified them by saying they are indeed hypotheses. Then we said, here's a conclusion you can draw from that using one of these basic rules of inference. Essentially, we're saying, hey, look, instead of building the whole truth table and stuff like that, I'm going to use a basic argument that I can prove using a truth table in a very simple way to derive a portion of the argument I need here without having to appeal to the full truth table of all the involved quantities. Yeah? We're basically breaking things down into bite-sized pieces. Okay, so now I've got Q. Now, perhaps I could do something else. What do you think I could do? Addition. That's a great idea. Okay, so you want to say perhaps you go, all right, what do we want to add to Q, perhaps? R. Yeah, okay. Q or R. So this is addition on 3, right? So I'm saying, hey, if I've got Q, then I've got Q or R via the law of addition. If addition seems weird at all, it's basically the same argument that like, well, it's not even, it's usually phrased, if you ever heard like an old guy say like, oh, it's hot out there, I'm a monkey's uncle, right? Something like that, like this kind of like old-timey weird, like, you know, it's blank true statement or something silly, right? Still true, it's the law of addition. That's like literally what the appeal is right there, yeah? If you have a thing that's true, then that thing or whatever the heck else you want to say, also true. Yeah? So basically that, hey, if you've got Q, then you've got Q or R. That's via addition. Now I've got Q or R. What I want to do next is appeal to my final hypothesis. So I will say, hey, wouldn't you know it, Q or R does indeed imply S. This is by hypothesis. Now, does anyone see how to finish it off? Maybe some modus ponens. Yeah. Number 6, we say S. This is modus ponens on 4 and 5. That is, I know Q or R, and I know that Q or R implies S, hence I know S. I have derived my desired conclusion, right? My desired conclusion was that S is true when these 3 things are true, and I've shown that that is indeed the case. Kind of nice, yeah? Sweet. Okay. Let's try some more. These can get a whole lot more confusing very quickly, especially when we're no longer working as neatly with just clear-cut, little ditties right here. So let me make sure I'm on the right page. I think I accidentally skipped a page in my notes. Okay, so the next one, example 2.6. See if you can do this one. This one looks kind of tricky. We'll have to use a few pieces together to do it. All right. Give it a moment, see if you can try it on your own. I'll do a little erasing in the meantime. God dang it. Okay. People making some progress in this one? You may perhaps need a couple more rules of inference, some of the ones we talked about at the very beginning last time. So if you recall, there's also 2 other very easy ones beyond these ones stated right here. And in fact, I can state them both right here by just getting rid of these columns, or these rows, and putting them on in. So that way you have everything at once to refer to. So here are a few more. The law of excluded middle, and the law of non-contradiction. So this example that we're doing now, the one that you've been working on, example number 2.6 in your note packet, asks you to prove that the following argument is valid. It says P implies Q and not Q. Therefore, not P. Okay. Solution. Well, as is almost always the case, almost always, we will start with one of our hypotheses. There's only one to choose from. Let's start with it. So we'll start by saying, hey, P implies Q and not Q. This is a hypothesis. Okay. We're going to label each step that we have. So it's step number 1. Step number 2, any ideas? Law of non-contradiction will certainly tell us some good stuff. So, actually, let me make sure I've said something correctly. I want to stay consistent with what I wrote in your notes. Actually, we don't need P here. I've been wrong with this. I said, let me be very clear. Neither of these actually require you. Yes, okay. Neither of these do you need anything. There's 2 equivalent ways of saying this. One of the ways of saying it is that you could say there are no required things right here, which is why they kind of look weird when expressed in a table. Another way to say it is that you could say, like, your hypotheses are the same as the conclusions you, well, no, let's just leave it as nothing. That is, no matter what the proposition is, these statements are true. Agree?
Yes.
You need to assume the truth of nothing. Sorry for writing that up there backwards. I'm being a little bit hasty. But either way, true. Okay. So non-contradiction, we immediately conclude this. Yes? Okay. Now, does anyone see an argument that I can apply to 1 and 2? That is, I have P implies something. I have not that something. What may I conclude then? We can do Toland's. Yeah. So I can conclude not P by modus Toland's, 2 L's, one L, on 1 and 2. Put my 1 a serif. There we go. Boom. Is this starting to make some sense? Feeling like slightly better? Yeah? Maybe? What if we did something nutso, like a crazy huge one? Yeah.
Why did, because in the original hypothesis, Q or Q and not Q is like positive, and now it's not.
Ah, so this part?
Does that change?
Okay, so notice when I'm saying this statement right here via hypothesis, I am not saying that the second part is true. What I'm saying is that this whole implication is true, right? Now the second part is just derived via the law of non-contradiction, which requires no hypothesis. That is, no matter what your proposition is, either the thing is true or not the thing is true. So the thing and not the thing is never true. That is, not the thing and not the thing is always true, no matter what the proposition is. You need not assume that the thing is true. It could be false. Either way, this statement will be true. So no matter what, you can always do this with any old proposition. So we say, hey, I can just do this with the proposition Q, right? Whether or not it's true or false, non-contradiction tells me not this is true. So it's not that I'm like getting this piece from the first one. It's that this is derived separately via the law of non-contradiction. Yeah? So from the law of non-contradiction, we produce not the conclusion of the implication, I guess, or whatever, like the antecedent of it, I suppose, whatever the right word would be, but the part to the right of the arrow. So once I know P implies thing, not thing, I get not P via Toland's, because that's what Toland's tells us. Modus Toland's tells us P implies Q, and not Q implies not P. Hey, what do you think? Meh? All right. Yeah. What about quantifiers? Uh-oh. This is where things maybe started feeling a little bit more confusing the first time around with propositions. As soon as we started throwing in quantifiers, things got a little bit more tricky. We'll need a few more rules of inference for quantifiers, won't we? Okay, so once we've got predicates, once we're quantifying predicates to obtain propositions, we need some rules to appeal to. That is something that we could prove in an easier fashion to, build our pieces for our larger arguments. Yeah? Building blocks for big arguments. We need some small arguments involving quantifiers that we can chain together to make big, complicated arguments involving quantifiers. Here they are. So this is 2.1.2. So arguments with quantifiers. What can we say here? We've got some names. And here are the rules. That is, we got like a little table here. Bruin. I hate this stupid thing. Flopping around on me. There we go. Okay. So, first one. Universal instantiation. In universal instantiation, the rule can be expressed as follows. I guess I'll write it like this. For all x p of x, therefore, p of c, whenever c is in the domain. That is, or in the universe. Or I'll say I'll say domain, whatever. The domain of discourse, the universe that the quantifier ranges over. Yeah? So, idea there is if you say, it's always raining here, and you say, is it raining here today? Answer is yes, right? If it's true that it's always raining, it's true that it's raining on Tuesday, it's true that it's raining on Wednesday, right? Okay. Universal instantiation. So a universally quantified statement, if it's true, then I can certainly instantiate any instance of the variable in the universe and obtain a true statement via instantiation. Okay. What about existential instantiation? So in existential instantiation, we say ex px, that is, there exists an x such that p of x is true. Therefore, p of c for some c in the domain. That is, if there is a c that makes this true, if there is an x such that p of x is true, then p of c is true for some c. Yeah? There's some number that you can take and actually pop it in there, or not maybe number, some value of the thing. It will usually be appealing to numbers in many things, but there's some value in the domain of discourse, some thing in the universe that you could pop in, instantiate, and obtain a true statement. Both of these let you effectively get rid of a quantifier by picking a value, instantiating a value. Quantifier disappears. This will be helpful when we have quantified statements because what we'll be able to do is appeal to these two rules, one of them at least, and pop out a statement with no quantifier anymore. Yeah? Okay, this is good. So we have two more. Universal generalization, which says if p of c is true for an arbitrary c in the domain, then our therefore statement is that for all x, p of x is true. So this is something you'll see a lot. Where you say, like, let n be an arbitrary integer, then prove a statement about something involving n. And then at the end you say, since n was arbitrary, therefore we may conclude that the statement holds for all integers. Right? So we pick like a, basically say like, pick whichever one you want. Look how it works. And you go like, since you could have picked anyone you wanted, nothing relied on your choice, and you got to the conclusion, it works for all the things you could have picked. Okay. So if your choice didn't matter, then the statement's true for all things you could have chosen. Yeah? These laws look weird to write out, don't they? Okay, finally we have existential generalization, which says that if P of C is true for some C in the domain, we may conclude that there exists X such that P of X is true. Specifically, the X would be equal to C, right? Okay, cool. These maybe seem silly at first. That is, when you look at them, maybe you go like, it sort of seems like you've just said the same thing twice. Like if you said, hey, P of C for whatever C you want, therefore, for whatever X you want, P of X. It sort of seems like you've just said the same thing twice, yeah? Perhaps it's the case, but effectively what we're saying is that if you can instantiate, like if the instantiation is true, irrespective of what thing you've instantiated, right, then it's universally true. If an instantiation is true for, if some instantiation of the predicate is true, then it is true that there exists a value for which the predicate is true. These maybe seem like obvious little points, but hey, we'll use them and chain them together in ways that will allow us to say much, much more complicated stuff. It's kind of, think of all of this stuff like Legos, right? Like if you look at any individual Lego piece, you're like, all right, it's like a little block, right? Okay. But you can build some kind of crazy stuff out of Legos, yeah? You just need more than one piece. So, same business here. Easy starting point, complicated ending point. Let's do an example. So let's show that the following argument is valid. For all x, P of x and Q of x, and there exists x such that P of x implies R of x is true. Therefore, our conclusion says that there exists x such that Q of x and R of x is true. So, if we want to go through and show that this is valid, what are we going to do? Okay, maybe before we start doing that, let's think about what this is saying. Let's look and make sure that this mess of symbols, this sea of notation, actually appears intelligible if read. So what it's saying is that no matter what x you pick, P of x and Q of x is true. And if you buy that for some x, it's true that P of x implies R of x, then there is some x such that Q of x and R of x are both true. Kind of following it through, it says that, hey, look, if both of these things are true, for no matter what value of x you pick, then certainly for whatever x exists such that P of x implies R of x, well, P of x and Q of x is certainly true, right? An and statement is true only when both things are true. So from this, we should be able to say, hey, look, P of x implies R of x. Q of x is also true. So we get Q of x and R of x. Do you start to see kind of how these things fit together, right? Or no, maybe not. I just said a lot of words. Maybe it's just a bunch of words. What do you think? Yeah? Nods? Some nods, some faces, some I don't like this, some it's a Wednesday afternoon. All right, or morning, mid-morning, I don't know. It's a time of day. So let's see what we can do. Who wants to give me a step?
For an arbitrary x in the domain of x, P of x and Q of x are true hypotheses. This would be our hypothesis.
Okay. So I think I see what you're saying. You're saying like start with like this and then pick like an arbitrary value. That's a reasonable thing to do. I'm going to make a little claim here actually, that if you're trying to do something like this with these two statements, if this one works no matter what x you pick, and this one only works for one x, we should perhaps pick the more restrictive one to start with. Yeah? That is, if we instantiate this first one, we may have instantiated it at like the wrong point, right? Relative to the second one. Yeah? Maybe let's start by instantiating the second one. So let's do something like existential instantiation. So if we start with, there exists an x such that p of x is true, therefore p of c for some c, yeah? We can take this second statement and turn it into a non-quantified statement, yeah? Reasonable? Okay. So, proof. We may end up having to go over to the next column, but that's fine. So first thing, I will start out with exists x such that p of x implies r of x. This is by hypothesis. Okay. Then perhaps I will do an existential instantiation. So let's say p of c implies r of c for some c in the domain. This is existential instantiation. On 1. Okay. Reasonable? So we get p of c implies r of c is true for some c. Now perhaps I'll reference the first statement. So notice this is itself its own line. For all x, p of x and q of x, this is by hypothesis. Now, what I'm going to do is I'm going to instantiate this universal statement at the same c value, right? Okay, so I'm going to say, hey, p of c and q of c universal instantiation on 3. Yeah? So I claim that this is an easier way to go about it, since if you had started with this one and then said this, it would not have been clear that the c you instantiated here was the same c that you do here. Yeah? That is, it would have appeared you're making the claim now, like if you had started with these ones and you had been like, oh, p of c and q of c. Which c? Like, it works for any one you pick, but you have to pick one. So which one did you pick? You just pick someone. It might not be the same one that you get to pick here, right? So what we're doing here first is we're saying, look, I can pick one here. Now, since I know I can pick one, I will use that one to instantiate this universal statement at the same place. Cool. That's well justified so far. All right, so now I've got the statement that p of c implies r of c. Yeah? And I've got the statement that p of c and q of c is true. Perhaps I could do something like some simplifications. Let's do 2 separate simplifications. How about that? Yeah? So maybe I'll go 5. I get p of c on 4. Simplification on 4 gives me p of c. 6, I also get q of c. For the same reason, I can simplify 4. Yeah? That is, If P of C and Q of C is a true statement, both of those things are true separately. Yeah? Okay. So now I've got P of C, and I know that P of C implies R of C. Is there a rule that now allows me to get R of C? Modus ponens, yeah. Modus ponens, modus ponens, R of C. And that's via modus ponens on 2 and 5. Okay, now I've got Q of C, I've got R of C. Is there a rule? Shifting my camera so I can point at it. Perhaps conjunction, P and Q. Therefore, P and Q. Yeah, same business here. Okay, let's do it. So I've got, good, switch the camera back over, 8. I can say, well, look at this. Q of C and R of C. This is conjunction on 6 and 7. Hopefully that's not too small of writing up there. I am running out of room in this corner, but we are almost there. Can I do something using one of these rules over here? I've got P of C for some C in the domain, so can I say that there exists an X such that P of X is true? Yeah? That is, can I take 8 and turn this into the quantified statement EX such that QX and R of X? Does that seem reasonable? So this is an existential generalization on 8. Make these like bigger surrounding parentheses. Okay. And hey, we did it. We started with our hypotheses, we performed manipulations on them, and we reached our conclusion. Nice. That's exactly what we wanted. Worked out wonderfully. And here we are at the end of class. Awesome. We'll do more next time. Have a great day. See you around.